All right, so hello and welcome. Howdy, here we are another day. Let's take a moment, make sure live stream is working. Let's see, give it a minute. For a few seconds. It's working. Deep breath. Okay, 15 seconds. Oh, it's working. Give it a minute. Nice. Very good. Okay, so continue from here. Oh, my soul. My soul. Just. I live a life of bitterness and pain. I have to say, it's tough. It's tough. All right. So I looked at this question. So let's get into what I'm working on today. And some days it can be kind of difficult. So yeah, I kind of made the screen a little bit larger so it's easier to see what I'm doing. The videos. Man. Some days are better than others. And I think, I don't know, I'm probably going to make a video talking about some things later, some things I want to do. But I'm sad about things is like putting it lightly. Things that are just, it's very painful, very bitter, very difficult. Anyway, so yeah, deep breath. Gotta move forward. Okay, so this question is kind of challenging in my opinion. It's rated medium, which I think might be like on the border between medium and hard. I don't really know why it's considered medium. Like hardly anybody submitted solutions to this one. In fact, this has less accepted solutions than I have people ranked ahead of me in LeetCode. Meaning like very few people have solved this question. Very few people even attempted it. And of those people that solved it, almost half of them actually got it. This is a pretty tough question, I think. Most people just quit, basically, is what this means. Most people just looked at it. Probably like 90% of the people that looked at it just gave up. Which I think they say that on the internet. I've seen that other people, they're like, oh yeah, I solved all the LeetCode problems, and like the ones that I didn't know, I just skipped. So this one, yeah, this really has kind of a special, the solution that I came up with, it really is kind of unusual. It's very much unlike other solutions. So I came up with a solution that's, so here we'll read the question first, read it again. There are some stones in different positions on the x-axis. You are given an integer array of stones. The positions of the stones, call the stone an endpoint stone if it has the smallest or largest position. In one move, you can pick up an endpoint stone and move it to an unoccupied position so that it is no longer an endpoint stone. In particular, if the stones are at, say, stones 1, 2, 5, you cannot move the endpoint stone at position 5, since moving it to any position such as 0 or 3 will still keep that stone as an endpoint stone. The game ends when you cannot make any more moves. The stones are in 3 consecutive positions. Return an integer array answer of length 2, where answer of 0 is the minimum number of moves you can play, and answer of 1 is the maximum number of moves you can play. So basically, I spent the day yesterday, most of yesterday, just thinking about this, because it was kind of this is a pretty hard question, in my opinion. Pretty hard as far as like, it's not obvious how to solve this, and it's not obvious like what other problems this might be related to. At least the things I've seen already. And I've solved a lot of questions in my time. I'm probably at like a couple thousand. I have like 800 on this website, maybe almost 900 on this website, maybe like 600 on another website, and then like a few other websites, maybe like 3 other websites, probably 200 each roughly. So I'm definitely over like 2,000. I probably over like 2,200 questions or something solved. This is a very unique question, I have to say. It's a pretty unusual question. So, okay, what are some of the ideas? Well, basically, I think the first thing to do, so what I ended up coming up with is sort the stones, firstly, right? Because they're on the x-axis at these positions, and, the x-axis is sort of from left to right is sorted, right? So you could just start with source sorting. There's only 10,000 of them, so it's not the worst thing to sort, not too expensive. That gives you an n log n bound. Then I think I was able to come up with a way to do this in linear time once it's been sorted, and then also basically constant time for the second part. The first part's pretty sophisticated. It's a 2-pointer greedy solution, and I'll explain how it works. The second part is basically, and both of these are pretty much, I came up with algorithms that I think will give me those numbers, and then I just kind of tried to optimize those things, like try to come up with something that's fast and also gives me those answers, right? Second one, the algorithm can be kind of optimized out and just be done in constant time. So let's talk about those algorithms, what the idea is. So I'm not using MS Paint. Maybe I should be using MS Paint, or not MS Paint, but not using. I'll try to explain this. It's kind of tough. Not using. What's it called? Paint. It's like, I don't know if there is like a paint equivalent for Linux. I don't think I have that. Painting tool. I gotta install it. Okay. Let's see. So I don't have a painting tool, huh? Excuse me. Tux Paint, drawing program for children. Huh. Voxel Paint. Paint in 3D using voxels. So I don't know. Okay. Not sure what I did regarding paint. So yeah, okay, we're not gonna paint. But you could do something like the following. So the example that I had was like 2, 1, 3. I don't know. So the first thing to do is sort the stones. Second thing to do is to create the difference array, right? This is for calculating the first number. So once you've done that, you can get something like 5, 2, 1, 3, 6, 2, 1, 8, 9, 1, 2, 4 as a test case, an example. And this could be something like 1 with 5 in between would be 7, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 1, 2, 3, 4, 5, and then 7, right? So you would take whatever this number is, add 1 to it, and then add that to the previous number, right? So you'd add 3 to get 10, add 2 to get 12, add 14 to get 16, add 7 to get 23, add 3 to get 26, add 2 to get 28, add 9 to get 37, add 10 to get 47, add 2 to get 49, add 3 to get 52, and add 5 to get 57. Okay. So we have, this could have been the initial state, right? Actually, this could have been offset by any amount, any smaller amount. You could add some amount to these values, like 100 or something to all of them, and you'd still get the same difference array, right? Okay, so now with this difference array, the analysis is basically, that I came up with, is basically consider left to right using a 2-pointer solution. The numbers that you're going to keep track of are going to be, I call them S, C, T, and diff, which is T minus S, right? And the conditions that are important are going to be C greater than or equal to difference, difference greater than 0, difference equal to 0. Right, this is what's most relevant. And S is going to be this. So at each point, there's going to be a left bound and a right bound. There's going to be L and R as well. Variables L and R, L, R, S, C, T, diff, and then these conditions are meaningful. And L is going to be the left bound. and R is going to be the right bound of what we're processing up to this point. So S, it's going to be the sum. C is going to be the current position, current value, and T is going to be the number of elements that we've seen that are not in the sum, if that makes sense. So initially you'd have S is 0, C is 5, and T is all these other numbers. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So T is 11, S is 0, C is 5. That means that we can pop 1, 2, 3, 4, 5 of these stones in between this two stones that comprise this difference. So you can fit 5 stones in here, and this goes to 0. The difference is 0. The goal, by the way, is to make the difference array all zeros, right? All zeros. To make it consecutive, right? So we can look and say, okay, define S in that way, define C in that way, define T in that way, and then we're going to go left to right. So we're going to increment the right bound one at a time. And what will happen is we update C. So the next step we would say C is 2, S is 5, and T loses 1 element. So T becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So T is 10, then T goes to 9, S goes to 7, and C goes to 1. So that's kind of how we're going to move from left to right in one iteration. Eventually there's going to come a point where we stop moving to the right and then we start moving to the left, from the left to right. So we would actually add an element back to T now, update, keep C where it is, and then decrement S by the amount. So we want like 2, 1, 3, for example. That's going to be, I guess, 2, 1, 3, 6, we'll say, where 6 is the rightmost element. 2 plus 1 plus 3 is 6. That's S. T is 1, 2, 3, 4, 5, 6, 7, 8. So we have T of 8, S of 6, and C is 6, right? So T doesn't include C, and S doesn't include C. C is just like the rightmost element of the range that we're looking at. And the analysis is basically, look, we're going to take all these other elements on the left and the right side, and we're going to place them in between these other, and each of these numbers represents basically 2 stones and the difference between those 2 stones. But when you remove one of those stones, this disappears, right? It goes to 0. And you got to put that stone somewhere. So we're going to put, 5 stones here, plus 1 is 6 stones. So 6 stones go in here, and then you get 1, 2, 3, 4, 5, 6. So you're left with 6, 2, and 1, and all of these to the right would be actually gone, technically gone, as far as the understanding here, and the left side would be, this would be gone, and these would be all zeros, and we would just be left with 6, 2, and 1. And then the idea is, okay, how do we handle 6, 2, and 1 as efficiently as possible? Well, as it turns out, there's a little bit of kind of finagling that you can do, where you can move these elements in such a way that it takes exactly 3 moves to bring these all down to either removed or 0. And the way that would work is you could put these 2 stones between these 2 elements, I should say. These ones can be moved between the 2 stones that make up the 6, and the 2 stones that make up the 6. You can do it in such a way where you move 1 stone. If let's say it was x and x plus, let's say the stone positions are x and x plus, I think 7. It's got to be, where x plus 7 minus x is 7 plus 1 minus 2. Yeah, that's 6. So x to x plus 7, you could put those stones at x plus 2 and x plus 3, and now the stone at x plus 7 you can just move into x plus 1, right? And that would take three moves. A little bit confusing, but if you think about it, it should make sense. So you can handle these three all together in 3 moves. So you get a total of 1, 2, 3, 4, 5, 6 plus 3 is 9. 9 moves. And what happens after this point by the way, is the next thing that's important. So I'll explain like what's going on with this diff part, because that's kind of what I just described. It's depending on these values, there are different ways to kind of move things around such that you can get kind of the optimal ending for the maneuver. The next thing relevant here is if you go to if you have there's other conditions that are relevant here. Diff less than 0 is also important. I think that's all I really need. So I kind of really struggled with this question and thinking about it, quite frankly. This is pretty tough. This is pretty tough. Diff was t minus s. I think it's actually not diff less than 0 I need to worry about. Yeah, it's confusing. It gets confusing. I really struggled. Yeah, like I said, I really struggled with this, thinking about it. There's actually more to it than this. It's I think if C is less than diff. Or diff less than 0. I don't remember which condition is the when I would need to move the left side over. When that happens, we increment s by some x. We decrement s by some s. We increment t by 1. And then the diff is then we add 1 plus 1 and minus x. Right, the diff is going to be t minus s, so the diff ends up getting modified in that way, plus 1 and minus x, because it's related to s and t, calculated off of s and t. And then c stays the same. But why would I want to move the left side? Like, why would that happen? The reason is this. It basically is that the t and s have gotten to such a state where I actually can't fit all of those t values into s. Yeah, so that's the condition. So that does happen at some point here, which is 1. So that actually happens at I think like here. So it's, how does it work? Yeah, I can't fit all the t values into s. Is that what it is? I'm trying to think when I'm supposed to do this. I had another value called alpha beta gamma. Yeah, I think it's alpha beta gamma. I had a gamma, which was just s plus c minus t. And when that was less than 0, then that was another condition. I'm actually not sure. I'm not sure if it's just when the diff is less than 0, if that's when I'm supposed to move on the left side. That's another question here I'm not too sure about. In this case, you get, let's say we're looking at 1, we get 7, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Being able to fit 7, 1, 2, 3, 4, 5, 6, 7 into these 7 values here doesn't necessarily mean that I need to pop the left side, right? And actually S being greater than T is exactly when that's, T is less than S. And that means that diff, which is T minus S, that's going to be less than 0. That's actually not necessarily a problem because the, oh, that is a problem. Yeah, because, okay, yeah. So the C variable is very important because I'm not including C. Yeah, that is right. Okay, I got it right. No, I had it right the first time. Right. That's important. So if diff is equal, in other words, if all the T values can fit nicely, then it's possible to process C on its own. And I'll explain that in a moment. But if there's too many T values, right, if T is larger than S, it still may be possible to fit those values. Yeah, if T is greater than S, has to be greater than or equal to S. The issue is C has to be greater than or equal to the difference, what's left over. So if C is not greater than or equal to that difference, what's left over, then obviously you have to increase S. You're not gonna shift the left side. You're just not gonna bother. Like, you don't have a solution at that point, right? If T is too large, if T is way too large, T is larger than S, but even larger than S plus C, then you just don't have a solution. That's where you look at C greater than or equal to diff. But to move the left side, that's when you decrement S. That happens when T isn't large enough to fit an S. And that happens, basically, yeah, you have T is too small, S is too large. Because even if you put all these elements in on the left side, they wouldn't all fit on the left side. In which case, then you end up in kind of a weird state where, like, I can give an example of that, right? That would be like 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So this would be exact. And then if you add this 3 here, and now consider this 6, there's a 3 and a 6. All of these elements have been placed here on the left side. And then you're left to wonder, well, how do I process 3 and 6? Well, the whole point of this algorithm, this approach, is to specify exactly the elements that we're not going to pop off the left side or right side. So that's kind of like what I'm trying to do is I'm trying to say, look, there's only a certain number of elements on the left side, a certain number of elements on the right side that I could pop and push inwards. And eventually I'm going to get, and I could put them anywhere I want. I could put them on the right side, I could put them on the left side, whatever. And oh, that actually might be, this might not be totally correct, this algorithm. Oh no, I gotta think about this now. Shoot. I think I have to do a little more with this. There's one more detail here that I missed the other day. It's pretty, like I said, it's pretty convoluted, pretty involved. Not convoluted, but it's complicated. So anyway, so yeah, the idea is that I'm going to specify a certain section of elements that I might need like an S1 and S2. I'll come back to that, explain what's supposed to go on there. But anyway, so there's supposed to be a certain section of elements that I'm definitely going to put the other elements. Certain elements are going to get popped. Other elements we're going to place inside those elements, and then have a certain state at the end of all zeros and something on the right side. It's not 0, and then address that, and then that should give me the optimal number of moves. There's something really subtle here though that I missed the other day that I'll come back to, but we'll come back to that. But anyway, so yeah, so if I'm in a situation where t is way too large, then obviously I have to keep going to the right to increment s and decrement t, and that's when the difference is greater than c, meaning I can't fit all those elements into the last, or yeah, I can't even, I'll have elements left over if I try to fit them in on the right side. Excuse me. The other option is, excuse me. The other option is if the difference is less than 0, that means I can't fit all of these into the part that I'm supposed to fit it into. And then basically it's equivalent to, now I'm in a situation where, okay, I've got to actually like probably pop the right element or something. Like it's to, possibly pop more elements from right to left or left to right or something. And in which case that actually is just a different case altogether, right? And yeah, in that case you would just in that case I would pop the left side to reduce s and increment t. To make that difference, to change that difference. Trying to think if that makes sense. Yeah, you just don't put things into the left side. It's too many things in S. And so you keep the same value of C and then just remove that S or convert that to a T. Then the diff should be incremented, should be larger. And part of the question there, one of the ideas, so one of the problems here I just noticed is, I'm pretty sure that's correct. I'm pretty sure that's when you move to the left, from left to right, is when the diff is less than 0, then you perform that maneuver, and then you start going into, you just move the left side over of the range. So yeah, it's kind of simple, but not the easiest thing to understand or explain. There are a few more pieces to this as well. So like I said, C is always going to be on the right side. The deal with C is there's a few different cases that happen. So what can happen is that you move all of the other stones into those gaps, and then now you're left with something on the right side, and there could be a few different variations. You could have C has to be greater than equal to the difference, right? If C is less than the difference, then you're in a situation where you actually can't fit all of the stones, right? As mentioned, there's stones left over and they can't all fit inside C. So that's sort of a nonsensical situation. You would just go to the right and skip that. So when C is less than or equal to the difference, if C is greater than or equal to the difference, C is greater than or equal to the difference, that means that you could fit all of the stones in C and possibly either have nothing left over or have something left over, right? So in the situation that you have nothing left over, you're just done, right? You just basically fit all those stones in that gap and you're done, and you just return T, where T is the number of stones that you moved. If C is greater than the difference and the difference is 0, right? So if the difference is 0, that means nothing's left over after you put everything in. Difference is 0. If C is still, there's still something left there for C, then you return this kind of unusual return value, which is T plus the minimum of C and 2. Meaning if C is 0, then you're just done, you return T. If C is 1, then you can move the leftmost endpoint into that gap in one move and complete the algorithm. So that would give you t plus 1. So min of C and 2 when C is 1 gives you 1. And then finally, if C is greater than or equal to 2, then it takes only 2 moves to finish off that gap. And what you do is you just say if it has 2, you take the left element and put it in, like, let's call it like alpha at the end. If the right, that position of the rightmost element is alpha, the rightmost stone is alpha. Take the left endpoint, move it to alpha minus 1. And then because there was 2 gaps, so alpha minus 1 is a position that's open and alpha minus 2 is a position that's open, move alpha to alpha minus 2. So you just kind of do like a little small crisscross type of a thing. And that costs you 2. And then you're done, right? That's sort of optimal. So you get t plus min of C and 2. When C is 2, you get 2. When C is greater than or equal to 2, you can do the same maneuver no matter how far to the right that stone is right now, no matter how large C is at the end. No matter how large that is at the end, you can move it all the way to the right. Now, something subtle here is the value of C. Really, this min should be C minus diff, but if diff is 0, as I mentioned, it doesn't matter. It's just C, right? Diff being 0 basically means that all of the elements have been placed into S, and then C is the only thing left. Now, what about when C is greater than the difference and the difference is non-zero? In other words, there are some elements left over on the right side. Like in this case, there's like, if you go to 6, 2, and 1 here, you can do 1, 2, 3, 4, 5. 6 fits in 2, 1, 3, right? So you do 5, 1, so 1, 2, 3, 4, 5, 6, excuse me, 8 to 4 and 5. You could fit those 6 elements in 2, 1, 3, and then you have 6, 2, and 1 left over. This is an example of this where C is greater than the difference. The difference is 2, and C is 6. So in this scenario, you can just return t plus 1 because you're going to put these 2 stones in, and then this also has enough room to be maneuvered in such a way where it just costs 1 to handle this stone as well, which is not so obvious how that works, but it can be done that way. And I'm wondering, yes. Yeah, okay, yes. And that's kind of hard to see. Hard to think through and see, but it should work that way. If you have some stones left over after placing them in S, then yeah, you can actually maneuver them. The same kind of crisscross maneuver that I described. As long as C is greater than the number, there's at least one more stone available, one more position available than these, then you can always put, basically fit all of these into that difference, those gaps, right, from sort of right to left, until you have well, not right to left. It's like you have to put them in sequence with one extra spot open, right? And that extra spot is, you're just gonna take that last element and put it in there, and it ends up costing you exactly whatever's left, the difference plus 1, which basically is just all of t plus 1, right? So you just get t plus 1. Not the simplest thing to understand. Now, so what I have here is basically, and I think it's correct. It's basically, I'm going to test it to see if I have it right. I have to test more test cases, but basically, if C is greater than or equal to the difference, and difference is greater than or equal to 0, then you've got some subcases. If C is equal to the difference, return t. If C is greater than the difference and the difference is 0, return t plus min C and 2. If C is greater than the difference and the difference is greater than 0, return t plus 1. If the difference is less than 0, then we're going to move the left side over, right? That was, I think I described that before. If if you can't actually fit all the t values in the s values, then it's kind of a doesn't really. It's sort of a nonsensical test use case position to consider, because basically you have to pop something else, and so it doesn't work with those boundaries as described. So you've got to change the bounds. So if difference is less than 0, you move to the left side. Otherwise, you're going to move to the right. And that would give you a linear time total. You're going to take the minimum of all the returned values, the t, return when you return t, or t plus 1, or t plus min c and 2, whatever those values are. Take the minimum of all of those possibilities. There's one more caveat here, and that is the left side and the right side. The left side and the right side, what can happen is, instead of putting everything, basically you could do this left to right and right to left in the reverse direction. And I guess in theory you could swap your s values, like your c and s values, technically. Not swap them, but basically set c to this left. Left. Maybe you should do right to left. Actually, maybe it's right to do it that way. Yeah. So I don't think this is totally correct, this approach. There's a subtlety here that's not obvious. Interesting. I'm basically thinking, what if you consider the left side and the right side in tandem? Because you have a difference, as I mentioned, you have a difference of where you put all these elements, where you place them all, and then you've got something sort of left over to consider. You could have your leftover on the left side rather than on the right side. So C could be on the left side rather than the right side, and in which case you've got a totally different kind of set of things to consider. And that would be the same algorithm in the reverse direction. I could basically run the same thing twice, just reverse these elements. Yeah, make it a subroutine, run it in reverse. And so that would give me, like, 2, 1, 3, 6, right? For example. And the reason why this is significant is the element on the right side being the last element to modify, or the element on the left side being the last element to modify. That value of C, like, you could have t, you have t plus 1, or you have t plus min c and 2. So it could be a mixture of t plus 1, t plus 2. And when c is equal to the difference, in other words, when c is a little bit smaller, you just end up with t. When c is a little bit larger, you end up with possibly a larger value. Could be an extra 1 or 2 added. So yeah, if we consider, like, 1, 2, 3, 4, 5, 6, 7. Excuse me, 8 different values being placed here. If we put 2 here, well, it won't work if you put 2 here. If you put 6 here and then 2 here, then you run into trouble. So it doesn't really work in this case. But in theory, you could have basically the same thing, but these are different by 1 or 2 elements on the left or right side. And depending on which side you picked, it could be an improvement if you instead went on the left side instead of the right side for the last element to process. There's one more question too, as well. What if you had, like, 1, 0, 0, 1 as elements to consider, because you can actually handle in one move. No, that should be fine. That would be fine, because you would just do 1, 0, 0, and then the other 1 would just be an element that gets popped, and that would be handled fine. That would be handled correctly. That would give you diff is 0. No, yeah, you would that would be when C is equal to the difference. C is 1 and the diff is 1, and you would just return T because you would just push that. Yeah, that gets handled fine. I think I just have to also do the reverse case and reverse case. I think that's it. I think that'll be correct if I do that do it that way. I'm not entirely sure about this, by the way. I'm hoping that this is correct. This is, like I said, this is kind of unlike anything else you might see out there. This is a very kind of unusual solution, and a pretty unusual, not too unusual of a question, but a pretty unusual solution. It's basically trying to sit down and find a pattern that's unrelated to most things out there. Not really your typical question you'd see, I think. It's also indicative of like why so many people skipped it, because it's just these sorts of questions kind of aren't worth the time, in truth. This is getting into, I think I've said it before, I may have said it the other day, like there's a difference between fluid intelligence and crystallized intelligence, as they call it in sort of IQ testing. And this would be kind of an example of testing fluid intelligence, which is very, like, it really takes a lot of, I don't know, like it's way harder to solve things that are not known or not known to you, and you don't really have much to work with on the question. And by harder, I mean it just takes a lot more time. It can take a really long time and be basically impossible to solve. Arguably, that's kind of like how research is done in the first place, is that you don't know something and nobody knows it, and then you figure it out, and then now you've solved something new. Excuse me. And that's kind of like, I don't think it's really appropriate for like software developers to be doing that in their employment, that they're trying to like come up with new research on the spot. That's sort of, I think it's like mostly inappropriate. And the reason for that is like, that's typical of like a research role, like as a PhD research academic. It's kind of like an academic thing to do, more so than anything else. You can be part of an R&D department, but again, it's mostly academic. I think in practice, you should really be doing not as much academic work. I don't think it's a reasonable expectation to have your typical employee be expected to do what is effectively the work of a researcher, and not be told that like that's what they're going to be doing. Right? Like, I don't think that's fair. Like, I think they're all researchers. It's kind of like, well, then they all should be PhDs, right? Like, why would anybody be? And not only should they be PhDs, but they should probably be given enough time to come up with new solutions to things, novel things that nobody's come up with before. That's kind of what this sort of question gets at, is that like you're looking at something that you've never seen before, you don't know anything about it, and like you're being expected to come up with what's comparable to like new research. It may not be new research in the field, but it's new research for you. And I think that's kind of unfair. I don't like that. I actually don't like that. I think it's, well, I've really have been forced to contend with that. Think about that like things that are known, like in a textbook somewhere that you could read and remember, you could be asked that question. But if it's so obscure that it's effectively like new research that you're being asked to do on the spot, it's like, that's just not a very realistic expectation to have for someone. They're probably going to fail that. And like, that's not really the fault of the candidate, because like if they were told like, hey, you need to know this, go look it up and read it, like I'm sure they could do it, most of them. And then if they're expected to do like new research on the spot, though, it's very like, some of these things take quite a lot of time. Doesn't really work like that, I guess. Can't really just conjure up solutions like that on the spot. Some people could do it, but they don't. It's, again, even those people, it's not really conjured up. It's more so, usually it's something that they've been thinking about for a while, and they kind of just realize like, oh, you could do it this way. That's more of how things tend to go. It's if it looks like it was conjured up on the spot, it wasn't. It was something they've already been kind of aware of for a while, typically. So yeah, that's what this question makes me think of, like fluid intelligence versus crystallized intelligence, right? Sort of what it says on the wiki. But I don't know. I don't know if this is even correct, the solution I'm coming up with here. I'm hoping it is. I'm really hoping it is. Really hoping it is. If it's not, I'll be kind of disappointed. Sort this. We have a difference array. So this could have one less element. And we're going to say int size 0 is less than n. So d of I is going to be the right side, which is vs of I plus 1, minus the left side, vs of I. And it's going to be I plus 1. We'll call it M. And maybe that's fine. So now I'm going to have a loop with an R left side and a right side. And we have a while loop here. It's a for loop. It's a for loop. Okay. And then run the same routine twice. I could make this a lambda expression, but I'm going to inline it. Just copy paste this one here and here. It's technically duplicated code, but it's so it's actually there's a few things involved here. Yeah, it's min result. Come back to this in a minute. Excuse me. Okay. The number of moves we'll say is just like 10 to the 9th, I think, or a billion. 10 to the 9th is a billion. Yeah. Okay. All right. So left to right for each element, we're going to calculate S. S is 0. C is 0. And T, S, C, T, and diff. Okay. C gets updated each step. T is, so this starts off at M. It's the whole thing. Yeah, M. And we'll calculate diff also at each point. Is like S minus T, just T minus S is diff. And so C is going to be, C is R, and it's going to be D of R. I'm going to particular L value. Before I increment L, I'm going to decrement S by d of L, and I'm going to increment T by 1. That's when I increment L. And on the right side, I calculate this C. We'll come back to this C value. I mean, maybe C could be here. C is d of R. I'm not sure exactly what I should do with this, but can come back to that in a moment. And diff is going to be S t minus S. Interesting. I guess I start off at n minus 1 if I do it this way. So C starts off at d of R, diff is then t minus S, S is 0, t is n minus 1. Right, this is kind of the initial state. And then we say if C is greater than or equal to diff, and diff is greater than or equal to 0. I have these cases. If C equals diff, min result min of itself and t. C is greater than the difference and difference is 0. Then same thing or similar thing. Let's do int val equals not t, but yeah, we'll say t. Val equals t. Val equals t plus min of c and 2. This is kind of what I was describing before. And diff is greater than 0. T plus 1. Okay. If diff is less than 0, then we're going to move to the left side, we break. So this is while diff is greater than or equal to 0. Diff is less than 0, then we break, we go to the next one. Which means I don't actually need this. Okay. Interesting. Okay. And I don't have S increasing. So when I increase the right side, so first, okay, it's a little confusing. How I actually should write. So that's like the inner part of the loop, but how do I do this correctly? Because S, so when I'm moving to the right, so I pick a particular L value, an R value, and now I start moving R values. Have the initial state S is 0, C is d of R, whatever the R value is, and T is initially just m minus 1. Okay. After I increment R, right, this also should be r is less than m. Whatever that value of r is, that's what c should be set to. This is maybe, I don't know, actually. Let's put c up here. We'll come back to diff as well. All right, so I think C, all right, we'll come back to diff, yeah. C should be set to d of r. S, so presumably we incremented, so we should take the previous C value and add that to S. Previous C value, add it to S. I think this is before we increment R, right? Yeah, this gets really confusing, huh? Yeah, actually R could be off the edge, which would be confusing for C. Oh man. This is like, okay. Oh boy. I'm not sure about this. I don't think I'm doing this properly. Let's really think about how to like code this so it works properly. That's what I wanted to do. Oh, excuse me. And not to mention it's pretty involved. Not to mention I'm going to copy paste the code too, which makes it more confusing. Fortunately, finding the maximum, the other element, is I think a little bit easier. I'll explain how that works, but yes, it's pretty, jeez. Okay. Just keep trying, keep going. Just keep going, struggling through it. So after I increment R, that's when I want to update, or before I increment R, I can update. So I can increment S with C, and then decrement T, and also increment and update C to the next R value, or yeah, this current value of R. That's really confusing. I think I need to do this. I think this has to happen. And in which case, C could be like so. Right? And then after I do my processing, it's okay to do it once initially here and define the variable here. I think that's fine. So we get C at D of R. T and S have already been defined. We get the difference now. We do this calculation, and then we update. Now we're going to shift R over. So we update S with C. R should be moved over, and T should be decremented. I guess this all happens kind of at the end here. Could say C equals dr, and then do the same thing here. Just do it at the beginning of each loop. No, actually, well, R is not necessarily less than M, so you don't want to do it. You don't want to do it there. Okay. This is fine. This is all fine. Increment R, decrement T. I was thinking I want to put this over here too, but that's probably not quite right. Okay, as long as the difference is greater than or equal to 0, you keep looping. Right? Perform this calculation and then perform the update to S. Now what can happen is increment R, and yeah, this is a little bit awkward here. I'm just thinking about two cases. One, when we go all the way to the off the edge. I kind of forgot about that. Didn't really explain that. And then on the right side, and the other case is when excuse me, when this breaks, when diff is not greater than or equal to 0. But I already incremented the S value by C, right? So that can happen. Diff is greater than or equal to 0. Recalculate C, the difference, and S. So this, this is kind of interesting. I think difference has to be recalculated again. Also here. Something like this. So right before I increment R, right? Or when I'm incrementing R, I'm going to decrement T, I'm going to increment C is going to become basically that next R value. And then S is going to have that previous R value is added at the index of R. And then it's going to become considered. So C actually doesn't factor in when checking whether or not I should go to this next sort of position. Interesting. That's fine. I recalculate T minus S. Excuse me. So this is calculated once here, and then after that, S and T are modified, and then it doesn't need to be calculated twice. That's kind of what I'm thinking about this here. Okay, this looks reasonable. When you increment R, when R is greater than M, it goes off the edge of the difference values. Then basically this calculation happens in here, but for the on the left side. So I'm actually not sure what to do about that. I think when that happens, it's kind of nonsensical. It basically means that everything on the left side is going to be placed into the stuff on the right side. And there is no element on the right side. Yeah, I think actually at that point, I'm actually not sure about that one. I'm a little bit uncertain. basically means we went all the way to the right. And what am I hearing? What is that? What the hell is that? Hold on a second. I think I will be back. I'm not sure. I'm hearing something weird going on. Give me a moment. Okay. Okay, it's working now. All right. Yeah, excuse me. I turned off the mic audio on OBS, and I think it caused some kind of a problem. Yeah, I turned off the mic audio on OBS, and it when I turned it back on, it didn't go back on when I pressed the button. Okay, so the question is, what are we doing here? When I go off the right side, what does that mean? With this array, because I think I technically would want to do this processing on the left side as well, even with the right side off the edge, but it doesn't really make sense because I don't know. It doesn't really make sense because I'm supposed to have that C value on the right side. I think I described that before. And what does it even mean? Yeah, it's kind of an unusual approach here because that, like I said, that C value has to be defined for this to make sense. Oh. I don't know. I probably should. I probably should do this the other way around. Actually, I should increment R at each step, and then have a certain number of L values that get incremented on the inside. Yeah, it's something. Actually, I think I did this wrong. So this really should be R is less than M. I think this is the correct way to do it. I think I did this wrong. And this kind of goes on the other side. Yeah, because really it's not. Really, the way I've defined this is kind of I'm moving left to right for each value of C, right? And then I'm going to go right to left again with the values of C. And I think that's the way to do it. And updating S as I go. So S is going to get incremented by C afterwards. t gets decremented by 1. This difference gets updated, t minus s. Increment r to c, and then we're going to say on the left side, whether or not I should pop on the left side. That depends on, so for a given value of c, c is greater than or equal to that difference. So increment r. If c is greater than or equal to that difference, and the difference is greater than or equal to 0, so we could perform that check first. Right, and then we can say everything we need to do on the left side. So this is while diff is less than 0, going to increment L, and while L is less than M, because the left side could be moved down as well. Should really be less than R, I think. L should be less than or equal to R. Well, yeah, less than R, less than or equal to R. If oh, that's confusing. It's one thing to describe something in abstract, it's another thing to actually program it. Oh man. It's not that easy, huh? Trying to design a function that works. Boy. Gee. Of course. Yikes. So what about, okay, so I'm going to try to move c values from left to right, but then there's this left value that kind of stays behind. So perform this check on with s, c, and t and diff. And then after that, then I may want to increment the L value. Now I increment L when diff is less than 0. Right, so I've got to update, at the very least I need to update diff. And I'm going to update t, I'm going to s. So s, we're going to minus equals d of L. So if the diff is less than 0, then obviously this if statement didn't trigger. And I would say, all right, and I think I do this again internally for each L value as well. This again for each L value. So let's say L is less than or equal to R and diff is less than 0. So if L is less than or equal to R, L has to be less than R. Can't be less than or equal. If it's less than or equal to R, then I'm going to subtract that L value, and then I just have nothing to work with. So that doesn't make sense. We can only go up to R. Decrement s by d of L, increment t, recalculate the difference, and then check this here. So yeah, that moves the L value to the right, moves this from S, adds it to T, recalculates the diff, and then performs the calculation here that we described before. I think I'm going to make this a subroutine. Make this a lambda expression. Just call it F. Yeah. Okay. Gee. Okay. All right. Go back to that. This is no longer D. This is going to be a vector D of integer D M. And yeah, could be zeros initially. Could be zeros initially. Okay. So have something like the following. All right. This just becomes D begin and D end. Okay. How are we doing here? All right. Think about these things, huh? Sorry, I've got some other things on my mind too. I was thinking about other things that are like difficult, painful things to consider. Yeah, life is kind of hard, huh? Life's kind of hard, huh? Yeah, it's kind of tough, I have to say. Not always, but some days it's pretty difficult when I consider things as they are. I don't think I really use n very much. I think I just use m here. In which case I could just make that well, yeah, m is fine, and m, it's okay. All right. So anyway, this for loop, and it's kind of involved. While the difference is less than 0, update st and diff. Run this check again. Increment L. Keep going until the diff is not 0. So if the diff is not 0, I think I could just do this once, right? Because if the diff is not 0, this will exit, and then you'd want to check again. And I'm not sure I even need this because, again, if the diff is less than 0, it won't even enter this, and it will enter this one. If it's greater than or equal to 0, then it won't enter this. It'll go straight into the next one. So I don't think I need this up here. Don't even need that, right? If it's less than 0, then it'll just keep iterating here, and it'll be greater than or equal to 0 here. Interesting. Excuse me. I think that's right. That's not the most obvious thing, for sure. I don't know. A little bit odd how it works. Does it work? I wonder. I think it's right. I think it's okay. Okay, so yeah, pretty involved. Pretty involved. They may or may not be totally programmed correctly, and the idea might not be totally correct either. I think the idea is right, and I think it's programmed correctly, but I guess we'll find out after doing some testing. Probably some mistakes, usually some kind of error. And like I said, I have to run this twice and reverse the difference array because I've got to go left to right with C on the right side, and then right to left with C on the left side, which right to left with C on the left side basically is just going through the same array, but with the whole thing reversed. And that will give me the minimum result. And then the max result. The max result is a little bit less difficult, I think, because there's sort of two parts to this question. Like in our example, 52136218912 you don't even actually need to go to the difference array. You could just look at the original array. And what you end up with is these values. You can sort them and then look at them as kind of a large interval. And the algorithm, I think, to get the maximum number of moves is basically you want to move your endpoints to positions that are as far out from the center as possible, as far, sort of far from the center as possible, to the left or to the right. And the reason for this is that you basically want to have as many moves as possible, so you want to keep your stones as far as far away apart from each other as you can, just for as long as you can. And so since you're only moving one stone at a time, the only option is you only have so many options, right? So you could move there's a left stone or the right stone you could move. And once you've picked one, once you've moved it, you want to move it either all the way to the right or all the way to the left, depending if you move the left stone to the right stone to the left, whichever one you pick. Move it all the way in that direction. And what you end up with is that the smallest stone and the largest stone create an interval. So you can take the size of that interval and then say, okay, now my next move, if I went left to right, I now can move that stone on the right side to the furthest point on the left side. And you'll notice that the interval that we were considering changes by 1 on the right side, right? So the interval so each move, the interval is only going to decrement by 1 in size until the interval is totally collapsed onto all of the stones are in line with each other. So basically the math on that is just like, well, since if one move decrements the interval by 1, and that's the best you could do at each step, then that's the max. That's 1. That's going to be the maximum amount you can perform, and also the number itself is just going to be the size of the interval minus the number of stones in it, more or less. After you've made the first move, the number of moves you're going to have is going to be that amount. So it's like a relatively straightforward kind of argument. It's not too hard, but it's going to be basically you get the difference of the left side, difference of the right side, which we already calculated different differences. Take the smaller of the two. That's the move you're going to make first. Then when you do that, so the calculation you end up with, then when you do that, then you have the interval between the sort of penultimate stone, depending on which direction you went in. The difference between the penultimate and the outer stone, that interval size, so we'll call it alpha and beta. Alpha minus beta plus 1 minus, alpha beta plus beta plus, alpha minus beta plus 1 is the size of that interval. the number of moves is going to be each move after that point decreases the size of that interval, and you're going to decrease it down to all the stones being consecutive, which all the stones being consecutive is going to be the size of that interval is the number of stones. So let's say you have n stones. That would give you, yeah, I guess I do need n then. That would be, so the difference then between these two is going to be alpha minus beta plus 1 minus n, right? Yeah, if you had an interval like 3 to 5 and you wanted to go down to 3 to 3, 5 minus 3 plus 1 is 3, and 3 minus 3 plus 1 is 1, 3 minus 1 is 2. Yeah, it would take 2 moves to get down there. Is that right? Yes, that's exactly correct. So yeah, you end up with this alpha minus beta plus 1 minus n. And then here you can go ahead and add one more move because of the initial move from the left to the right side, which gives me alpha minus beta minus n plus 2. And actually, if you could even go further and say like there's an a left and right interval size, different size, right? So LD and RD, we'll say. You want the min of LD and RD. I think you can rewrite this expression in terms of those. So if you have alpha and beta now, let's just say like min and max of stones. So S sub min and S sub max, right? Let's do it this way. So S max minus S min plus 1 is the whole interval. And then I said we're going to take the smaller of these differences. So subtract min LD RD. Which is going to make that interval smaller by that many stones, minus 1 more, because the stone itself is going to get pushed into that interval and basically disappear. That's going to be the interval size, alpha minus beta plus 1, and then you subtract n and add 1 to that expression. So you end up with S max minus S min minus min of LD LR RD minus n plus 1. Quite an expression. So max result is going to be the following. The max element and min element is going to be, so these are already sorted, VS. Let's actually calculate this before we do these other things. Excuse me, it's going to be VS of this max is VS back, min is VS 0, and also assuming these stones have at least one element. Yeah, there's always at least one. It's actually always at least 3. Minus the minimum of LD and LR, which is D begin and D end, or D0 and D back, whichever is smaller, minus n plus 1. Whew. That's the max result. And that's basically using a it's basically using a an algorithm for the maximum result, and then assuming that's correct, and then also looking to pretty much optimize it, like make it, run it, what the result would be if you ran that algorithm. You can calculate that in constant time if what I described is all correct. So yeah, this seems to be one way of doing this problem, approaching this problem. Possibly correct, possible way of doing it. Let's see. See if I have the right idea. I could be wrong. Oh, of course. Oh, I totally forgot. Val is T. I need to update min result, the minimum of itself and val. Forgot about that. Yeah, and I have to go through quite a few test cases to see if this is the right idea. Still wrong. No. 2, 1, 2, 2. Is it min max? Yeah, it should be min and max. Oh, it's awkward. It's just the wrong idea. That would suck. This should be okay, a little bit better this time, but this one, I'll put 2, 1. What is going on with that? Yeah, they both could have errors, I guess. Let's see. Let's look at the maximum thing, because I was just doing that. Let's see. 3, 4, 5, 6, 10. 3, 4, 5. 3, 4, 5, 6, 10. 1, 2, 3, 4, 5. Okay. That difference is going to be 3. Oh, I did the difference wrong. Actually, that's not right. That's probably has something to do with it. This difference is -1. I did that wrong before. Described that incorrectly before. So it's the next value minus that -1. It's how many stones are in between the two of them. Not Oh, now it's right. Okay. Yeah, that was a mistake on my part. I forgot about that. Didn't describe the differences correctly. I kind of explained it before, but I didn't. I just forgot that there's an extra -1 there, because it's the number of spaces between the stones. It's not the difference between the stone positions, which is a slight caveat, a slight difference, right? Because if you have a position at 3, a position at 6, the number of spots between them is 4 or 5, which is 6 minus 3 plus 1 minus 2, which is 6 minus 3 minus 1. Okay. I was going to say it should work in these test cases, because it's sort of designed to work in those test cases. But for more complicated test cases is where it gets interesting. All right. Let me see. How are we doing on time? Yeah, hour and a half. Spent quite a bit of time thinking. Yeah, it's pretty challenging, this question, I have to say. All right, so I want 10,000 numbers from 1 in a billion. All right. Whoa. Okay, let's try to write an awk script, and we're gonna do the following. So it's gonna be 1 for loop, and it's gonna be I is, let's do between, well, I could just do 10,000, I guess. Well, let's do 10 first, right? I is greater than or equal to 0, or I is 0, I is less than 10, increment I. We're going to print rand converted to an integer, and we're going to also srand. And it's going to be multiplied by a billion. I don't know if I can do that in awk. And then tr, well, let's just do this first. It works. Well, tr new lines with commas, and then said I want the last character to be empty. Add a new line character at the end. And then I want to also echo this and add these characters at the end. Okay, there we go. So let's set the script with some. Yes, that actually worked. That's kind of cool. Wasn't expecting that. Let's see. I can improve this a little bit. So I want 1 plus this value to a billion. It should be a billion minus 1, right? Yeah, it's a little confusing, but the size of the range, it's a billion minus 1 plus 1. And this doesn't go all the way up to 1, I think, the rand. I could double check. Looking for aux rand. Oh, I don't know why I'm doing that. Arc functions. Between 0 and 1, it could be 0, but it's never 1. Oh, okay, got it. So it's never 1. Okay, nice. That keeps it simple. Oh, it's correct. Because it's never 1, that means that what I had before would be from 0 to a billion half open interval, right? It would not including a billion. If I add 1, now it's between 1 and a billion. Okay. So now let's do like 10,000. And let me copy paste this. Holy. It's a way to do this a little more efficiently. Put this right into the clipboard. I don't know. Oh boy, this is take a lot of time, huh? Oh my. Copy. Next test case. Cool, it worked for the 4th test case. I'm gonna try some unusual test cases to see. So this will give me an idea of the speed. Also, it's correct or not. Oh, it's correct in that case. 3 milliseconds. Wow, that's quick. Cool. That's encouraging. All right, let's try. Let's do like 10, but let's limit this to like 10. Also 10 elements. Let's do like 110. Something like this. Try to get some unusual test cases going. Then maybe we'll do even tighter. Go to like 3 elements. Oh, it's wrong. No. Oh. Negative 89. Oh, hold on. Hold on. Okay. Oh, sorry about that. I don't typically expect people to be watching the stream. No offense to those that are watching. It's kind of often that I don't have many viewers, so I'm usually okay with like leaving the stream and doing things. And I'll just put up the video later. Actually, I think when I live stream on YouTube, it just automatically has the video ready, so it's fine. But yeah, just a few minutes of chatting with my family. Pretty sad. I think I need to go lay down for a while. It's like life is very hard. Life is brutal. It's a bitter, brutal thing. Oh goodness. Yeah. Anyway, we'll come back to that another time. So it looks like I had the wrong answer here, which is kind of unfortunate. I was kind of expecting something to go wrong. No, this is kind of interesting. It takes. What happened here? So first things first. -89, the maximum number of moves. How did it get -89? Where did that come from? What? -89? What? And this didn't come up with 0. Deep breath. All right. First things first. What? Why does this have -89? Where did that come from? What is going on with that? That's number one. Number one. Number two, I think my algorithm does not work correctly if the I think it's because I have duplicates. Oh, that's why. I didn't even think about that. Okay. I don't know why I didn't even. All right. You know what's wrong? This is supposed to be the differences, not the stones themselves. I totally didn't even think about that. Okay, well that's fine. I can do for the stones themselves. I can do a loop j, and then just say j plus equals int of 1 plus 3 times rand, or 10 times rand, and then print j. Could do something like this. It's fine, I think. Oh, can I not do? Can I do multiple variables in the for loop? Okay, I guess not. There we go. That's more of what I was going for. So, yeah, I mean, this should be an invalid test case, actually. Okay, I was gonna say, I was like, what is going on here? Why is this wrong? It's not wrong as much as it is just an invalid test case. I didn't really think about. Breathe here, breathe. It's gonna be okay. It's gonna be okay. All right, let's do like 1 to 3. Pretty sure the sorting works fine. I don't think I need to worry about that aspect of this. Okay, boy. Gonna remove all these test cases. Okay. Where's some other ones? So it looks like I might have gotten it. May have gotten the right answer. I don't want to get too ahead of myself here. So let's go now to some zeros as differences. Right. Actually, no, it's got to be at least one. Excuse me, it does have to be at least one. Let's do another one. Let's do like, I don't know, 1,000 for this one. Like being able to generate test cases with simple awk script. I think it's pretty cool. One awk one-liner. Oh boy. Okay. Let's do a little more dramatic. 1,000. Okay. And then I think and I'm going to try to just get some random values again. You know, I'm not so sure about this. I'm a little bit skeptical here. Let's try something like a little tighter. 1 and maybe 2. So it's gonna be 2 and 0s. Yeah, this is good. Let's do this one. This one's good. This one could have quite a few things that are next to each other. Yeah. Okay. Oh, it's wrong. Oh no. Oh. No. I was so close. No, say it ain't so. No, come on. Really? No. Oh, it's bad. Ouch. Oh. I'm gonna do it on time here. It's a good thing I didn't submit this. Yeah, you gotta test your code. You gotta fuzz it. Fuzz the code, it's called fuzzing. No. Oh, no. It's bad. Missed something important here. Oh. No. Let's do like 100. Maybe I can get the same issue with smaller number of. Oh, it's bad. Smaller number of elements, and I can kind of do it by hand, try to figure out what's wrong. Yeah, I think the sorting is fine. It's just there shouldn't be any duplicates. Gee. So there's kind of a subtle thing going on here that I just basically missed. What about this? Let's make them really close to each other and see if that does anything. I need to get a failing test case that's small. Small failing test case. So you can really see why it's failing, what I'm missing. No. All right, let's modify this one. Let's like cut it in half, see if it still fails. Some binary search here. Say it ain't so. Say it ain't so. Alright, something like this. See how far I can get. All of these are still correct. No. Alright, what about the other way around? I don't know, man. I don't know. Now it's correct too. Don't tell me that. So if I cut away half of it, it's correct. The other half, like it has to be exactly 1,000 elements. Gee, of course. No, this is so difficult. Oh, it's rough. What if I remove some of these elements? It's still wrong. Let's try removing a bunch, see what happens. No, it's correct. Oh my goodness. You've got to be kidding me. Really? Remove one element. Just one. You're kidding. Really? That one element at the end caused the whole thing to screw up. That's crazy. Are you serious? Are you kidding me? What? What? 2527. 2531. What is going on? You gotta, that's unbelievable. Absolutely absurd. You're kidding. So it's literally the last element is what makes it go from failing to not failing. What is going on? Huh. Well, that's bizarre. Oh no. Well, that's fine. Didn't mean to click that. So yeah, it's wrong in some cases. It's very close. So I got 587, it should have been 586. So from here to here, the only difference is one element. 2527, 2531. Of course. I mean, of course. Excuse me. Oh, you gotta be kidding me. Oh, very tempted to try to work on this locally, to try to work through like where exactly it's wrong. But this is crazy. This is crazy. What happened? What? What is this? What do you mean? What do you mean? 2527. All right. 2531. So, oh man, it's rough. All right, let me think here. Take a moment. 2527, 2531. Why? So 585 works, and 586 should work. Basically, the suggestion is that you can move this last stone somewhere. My algorithm says takes 585 without that stone there, and then I need 2 more iterations with that stone. Okay. No kidding. Gee. Well, I don't know, man. Does this have something to do with it? Wonder if it's this. This is the problem. Nope. Not the problem. Does this matter? I feel like I'm just missing some parts here. Some possibilities. Oh. No. I don't know what's wrong, man. I don't know what it could be. I don't know what it could be. I don't know. Why? Why? Forgive me. Sorry, I'm thinking about things that are kind of sad, frustrating, bitter, very bitter things. What is going on here? So this is like really not obvious why it's not right. Something's got to be very subtle, very slight, incorrect thing. You gotta be kidding me. No. Wonder about this. Wonder if it's this. I don't think so, but maybe that could be an issue. Nope. Not the problem. Of course. Why is this happening? What is wrong? You gotta be kidding me, man. No. No. 587, 586, 587, 586, 587, 586. It's a tough one. It's a tough one. I don't know what to say. I don't know what to say, man. So close. So close. No. This is like a very large test case too. Can I get the same effect with a smaller test case? Is that possible? What is happening here? The only, yeah, it's if I just remove the last number, then the algorithm works fine. All right. How about if I just make it one smaller? I don't know what to say. I don't know what the problem is. Did I get it? Oh, still wrong. Okay. What if I bring this down 29? Okay, well, that's good information. Just always wrong if there's one extra value at the end there. 28. How about that one? I don't know what is wrong though. I don't know. So for some reason, adding this extra stone causes one more calculation to fuck trigger. I wonder if these are wrong. It could be this. Well, okay, I could maybe try this. Oh, that's it. Just updates twice. What? What? $501, 500. LR 588, 587. That's it. 410, 438. Oh. Interesting. Huh. L needs to go a little further, I think. These two. 27. 31. Also, I think I need to go outside and walk around a little bit. Not getting enough exercise. bodies physically. You know, I was kind of wondering that before, if maybe the diff value is not the thing I should be mostly concerned about, diff being less than 0. I think it's maybe, it's actually when C is less than diff is really when I should be moving left to right. Or the diff value is less than 0. I'm wondering if I just need to move L a little more. No, well, that's confusing. S T diff, something like this. I don't know. I don't know. Just gonna say I don't know. So, okay. L is 0 to 410. So these first elements up to the 410th element. There aren't that many elements. Case 4. I don't actually know how many there are. But I get up to 410. And I say, all right, an update occurs. Got this value C. I should probably point out what C is as well. I'm not entirely sure what to make of this. Don't know. So let's also say first and second. So these are delineated. Also, if it's going left to right or right to left, it's relevant here. Oh, okay. So yeah, it's both. It's the first time. And yeah, okay, it's fine. So it works in the first run. 0 to 410, 587, 588. Diff is 1, C is 1. Diff 588. So from 0 to 410, which is way down there, I don't know, it's like 1600 or something. I get S, which is not 587. That's not correct at all. This is wrong. What? 587? Huh? No. That's like the first 10 elements. What is going on? Or 20 elements, something like that. Oh, it's the difference. Excuse me. Yeah. I'm sorry. I should be looking at the difference array. Yeah. I'm so used to thinking about the difference array. No, that's right. It's way down there. The differences. Yeah, the differences sum up to 410. 587. Okay. 587. Okay. So we have a diff of 1. C is 1. That means there's one extra element, and Okay. So yeah, we just get T here. Get all the elements can be placed. Diff is 1, C is 1, T is 588. Yeah, you would just return T. If diff is equal to C, then you could just place those last elements into C and you're done. Okay, and then we move over a little further, adding and removing elements, difference elements, and then we get S is 585, T is 587, difference is 2, C is 2. Okay, so here's a question. I return T. Yeah, diff is equal to C, return T. There's no other updates that occur. And this one's incorrect. Somehow I can do 586. It's not obvious at all how I could do 586. I don't know, man. I don't know. Gee. Okay. What? Excuse me. If I remove this element at the end, then I get 500 and 501 a little bit earlier, right? This case 5 doesn't have that element there. 2157. Wait, what? These are different test cases. No, case 5 has a lot fewer things. 25, 27. It should be 6 and 4, or 8 and 6, I think. 25, 27, and 8 has 25, 28. Yeah, 6 and 7 is what I want to look at. 6 and 7. So 6, 25, 27, 7, 25, 31. 6. So without that extra value, things go a little bit further, and we get to 585. Yeah, we get to this point. So these 2 points, these various points. Come back to this in a moment. Whereas with that extra element, we don't go to those points. We just go straight to these 2. So yeah, I mean, I guess I don't know what to say. What happened here? It's a question. What happened? It's all in the first round. I don't know. I don't know what's going on. Excuse me. How can I do this? I mean, it would be kind of challenging to do it by hand. 586. Apparently this can be done with 586 instead of 587. It's very close, but it's you know what? I think if the diff and C are equal to each other, then I think it's not. Maybe that's what it is. The calculation is slightly off. You don't return T. Do you return T? Do I return T? kind of had a similar issue. Excuse me. Excuse me. I kind of had a similar issue before where it was S and like S plus 2 or S plus 1 or something. Like it was just slightly off. I couldn't figure out why. Okay. Excuse me, does this give me 587 or 586? This update. Is this update supposed to be 587 or 586? That's my question. I don't actually know how they got 586. What I'm wondering, what I'm thinking is, no, the right to left solution should work fine here. I was thinking maybe there's an issue of like the last element being placed somewhere where C is 1 and the diff is 1. And no. No. Oh, excuse me. Oh. Three, 4, 5, 6, 10. Diff less than 0, C less than diff, or diff less than 0. I don't know what's wrong here. Can't see it. Don't see it. I could try to do it by hand to get 586, but that's really not obvious at all. There's got to be some assumption that I made here that's not correct. There's something that I wrote. It's kind of unlikely that I implemented this incorrectly because there are most of the test cases are passing, almost all of them. This is like a very large test case that's failing, which typically when that happens, it's like a really subtle thing with regard to the algorithm. The algorithm itself has there's some assumption there it's not quite right. Gee. I could run some debug code. Debugging. Run some debugging code. Oh man, partial sum. Okay. Partial sum. Input, output, into the output. So input, input, output. Okay. It's going to be D. Is that a vector? I think it's a vector. Yeah. Prefix. I hear my dogs. I don't know what's going on here. S is going to be prefix of J, I minus prefix of J plus D of J. I think that's how that works, right? Yeah. That should be fine. Then we're going to say int T is going to be M minus I minus J plus 1. And then diff is T minus S. And we're going to say int result brute force result excuse me, if I think this is the one that's very large, the second test case. Nope. One of these is huge. Maybe they're all not that big. I don't know. I don't know. I'm going to try to brute force this. Should take a lot longer. My TLE. Okay. No, not that long. Not bad at all. Wait, what? Should, oh, okay, well, anyway. Oh, okay. Yes. So I got the right answer, the brute force. Okay. I'm on the right track. Oh, I don't know what happened there. What happened there? Okay. Don't have to worry about that. Oh, that's not right. Uh-oh, that's not correct. So the brute force is not quite right either. What is going on? Uh-oh. Uh-oh. What is going on here? The brute force solution gets the right result sometimes. Doesn't get the right result other times. Uh-oh. 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 What am I to make of these things? I don't know. Gee. Gee, I don't know. Oh no. Sometimes the network also kind of drops. It's going to reset my test cases, I think, which I don't want. Internal server error. Whoa. Whoa. It's a little odd. Oh, internet connection's okay. The internet is okay. Nginx 403 forbidden. What is going on? What is happening? Is the live stream still going? Let's see. Hello, hello, hello. Live stream still going? Yeah. Let's see. Hello, hello, hello. Live stream still going? Live stream's working. Whoa. Whoa. What is happening? 403 forbidden. What does that mean? What is that? Oh man. I wasn't prepared for that one. What is this? HTTP 403. 403? What does that mean? Fuse is to authorize it. Jeez. What is going on? May have to make a part 3 here. What is going on? Why? Why? LeetCode. Okay. Okay. Maybe I have to sign in again? I don't know. Didn't. What is happening? Oh my goodness. I think I need to sign in again. Yeah, I think that's the issue. It's a little weird, a little strange. Yeah, let's sign out. Let's do that. Try again. Yeah, something really weird's going on. I think it's probably my internet connection is having some issues. I saw that the other day too, some website. I don't know what it was. I forgot what it was, but yeah, I got a forbidden something or other. I might need to sign out, and then also I don't even know. Okay, hold on. Let me check my internet connection, make sure that's not the issue. Oh, that's fine. Internet connection's fine. I want to sign out. Sign out. Try that. I may need to clear my cookies or something. That could be it. I need to come back to this. I don't know what is going on here. Yeah, it's having a hard time. Oh my goodness. This is like I might just make this part 2, part 3, part 2. Down from maintenance, pages missing. Is that true? Is LeetCode down for maintenance? I get the feeling they're not. Is LeetCode down? That would be kind of annoying. Uptime.com. Up down radar. Site outage. Is it down? It's just down. Down unresponsive every other day. Is that real? I can't get onto the server at all. Like nothing. I can't get. I think I need to clear my cookies. I think that's the issue. Sometimes sites have a hard time if like your cookies get messed up. I think that's it. I think what I'm gonna do is I'm gonna stop the stream here. Try whatever thing I could think of, imagine. Maybe it is, I don't know what's going on. Maybe the site is having a hard time. I'm trying to sign out. It's just not working. Oh my goodness. It's like, what is going on? Okay. All right. Register, sign in. Okay, let's go back. Should be signed out. The reason I don't want to clear my cookies is because I'm pretty sure it'll cause issues with the live stream. Some kind of issue, which would be unfortunate. Okay, so I signed out. Let's try to sign in again. Forbidden. Okay. All right. I don't know what's going on. One more time. Sign in. Gateway timeout. Host error. Browser, Cloudflare, host. I think LeetCode's having a hard time. I think it's specifically LeetCode that's having issues. Yeah, my internet connection's okay. I'm able to reach other sites. I think it's actually LeetCode that's having a hard time here. Forbidden. Is it down from maintenance? I don't know. All right, I'm going to make this a part 3. We're going to stop here. Oh, we're going to go ahead and stop here. I need a break anyway. That was like, I was thinking about writing the code locally. I think I saved the code. It's kind of unfortunate. Let me just see. What is this? This is like LeetCode 10, I don't know, 1040. There we go. I have my code saved locally, which is good. Okay, I'm gonna stop. I'm just gonna stop. Stop and just take a break. Come back maybe later. Yeah, I don't know, something's wrong. I guess maybe I should test this locally, the code. Try to figure out what's wrong. Something's wrong with my algorithm, my approach. I don't know. All right, I'll stop here. Take a break. Good time to take a break. All right, thank you.